This is lecture 7 in BBSP 710. Today we're going to be discussing graphical methods for summarizing data. The first question is, why do we graph data? And the main reason is that if you're trying to visualize your data and see patterns in your data, identify outliers, other or potential source of bad data, or just get an idea, is the data skewed, is it symmetric, things like that. It's much easier to see by graphing the data than by looking at a numerical summary typically. And it's also very easy to do with modern computers, particularly R. So, in my opinion, whenever you're doing any type of data analysis, one of the first things you should do is graph the data using the most appropriate graph and look for potential patterns and look for potential patterns and other interesting features about the data. A couple things to keep in mind when graphing data is that it's not always obvious which graph is going to be the most informative for a particular data set. So, particularly if you're planning to publish the results, you'll want to try several different types of graphs and then report the graph that does the best job of highlighting the features of the data that you care about, and make sure that you label your graphs so that other people can read them, or particularly if you're planning on turning them in for your homework or anything like that. Anyway, an extended example for today's class is a data set of chicken weights. There was an experiment conducted to measure and compare the effectiveness of some various supplements that could potentially affect the growth rate of chickens. There were 71 chickens in this experiment, and each of them got one of 6 feed supplements. If you want to try the examples in this lecture yourself, this data set is built into R. It's called ChickWeights, CHICKWTS. And first we're going to discuss graphs for categorical data. You can graph categorical data using tables, bar charts, pie charts, or dot charts. Usually tables tend to be the most informative, but particularly if you're preparing a poster or something and you want eye candy, sometimes you'll want to use some of the other ones. So the simplest, as I said, is a table. The command in R is table. So the first thing I do is I attach the chick weights data set, so I don't have to type chick weights $feed. I can just say feed. To get a table, I could just go table feed. It says in this particular data set there were 12 chickens that got casein, 10 that got horse bean, 12 that got linseed, and so on. Hopefully it's reasonably self-explanatory. But if you want something that looks cooler to put on your poster or something like that, you can use some graphical approaches. In particular, you could try bar charts, as illustrated here. Bar chart, once again, is hopefully fairly self-explanatory. The y-axis here is just the number of chickens that got each type of supplement, and you can see a different box for each different type of feed. To create bar charts in R, the command is called bar plot, and I'll explain these parameters in more detail on the next slide, but one thing that's kind of counterintuitive that you need to pay attention to is note that you say bar plot table feed rather than just bar plot feed. If you just say bar plot feed, it'll give you an error. I forget what it does exactly, but it doesn't work. You need to do bar plot table feed, and then you can specify the y-axis label and the main label at the top of the graph. So on the bar plot command, as I said, the syntax is bar plot table feed, not bar plot of feed, and the ylab and main parameters to bar plot allow you to label the y-axis and the heading of the graph. As I said, you should always do this if you plan to put your graph in paper, or you plan to put it in homework or something like that. The next type of graph that you may want to do, although I advise against it as I'll discuss later, is a pie chart. I assume you've all seen these before. A pie chart just is a little pie where the size of the slice of the pie is proportional to the number of observations in the data set. To create a pie chart in R, the command is pie. Once again, note that the syntax is pie table feed rather than just pie feed. And you can also give, you can provide the header for the graph by using the main parameter for the pie command. And the help file in R said it quite nicely. Says pie charts are a very bad way of displaying information. The eye is good at judging linear measures and bad at judging relative areas. A bar chart or dot chart is a preferable way of displaying this type of data. In my opinion, if your objective is to provide a good illustration of your data, you should, I will stop just short of saying never use pie charts, because bar charts and dot charts are almost always more informative. The only situation I can think of where you might want to do it is if you're giving a talk or a poster or something like that, where you're just going for eye candy and it's not going to be published in a paper or anything like that. If you do that, then maybe you can go for a pie chart, but even then, I think bar charts and dot charts are generally preferable. The final type of graph for categorical data is called dot charts, as I said here, and it just looks like this. It's similar to a bar plot, only you do it with dots rather than bars. And again, hopefully it's self-explanatory. You can see that there's 12 chickens with sunflower, 14 with soybean, 11 with meat meal, and so on. To create a dot chart in R, the command is called dot chart. Say dot chart again, once again, dot chart table feed. You can give the x-axis labels and the label for the heading using the xlab and main parameters once again. And as I said before, generally speaking, it's preferable to use bar charts or dot charts than pie charts. To me, pie charts are just eye candy, but they generally don't do a good job of summarizing data. Dot charts can be more informative or more misleading when the differences between the groups are small. If you saw the x-axis label for the dot charts for the chicken seed data only went from 10 to 14, so it's easier to tell the small differences in the sizes, but it can also give the impression if it were like one group had 1,000, one group had 998, another group had 1,003, for instance, the dot chart would help you see these tiny differences that wouldn't necessarily show up on a bar plot, but it could also give the impression that the group with 1,003 has far more observations than the one with 998, even though in reality there's very little difference. When there's a huge number of different categories, you may want to combine them, particularly if some of the categories are small. Oftentimes, for example, if I'm summarizing race, if you draw a sample from the United States, particularly from a place like Chapel Hill, you'll typically get a very small number of races like Native American or Pacific Islander or things like that. So we usually display our race data as just like Caucasian, African American, Hispanic, Asian, and other, where anything that's not one of those four racial groups gets lumped into other, just so you don't have a long list of categories with only one or two observations in them. That's the end of the discussion on graphing categorical data. Now we're going to discuss graphing quantitative data. And if you're graphing a single quantitative variable, the three types of plots that you will use will be stem and leaf plots, histograms, and box plots. First of all, I'll describe stem and leaf plots mainly for historical reasons. In my opinion, they're somewhat obsolete. Once upon a time, stem and leaf plots were fairly popular because you could make them easily even if you didn't have a computer with fancy graphics. But now that it's trivially easy to create box plots and histograms in R, they're almost always better. So I'm never going to ask you to do this in this class, and I don't recommend that you use it to summarize your own data. I'm only giving you this information so that if you see a stem and leaf plot someday, you know what it is. So to create a stem and leaf plot, I'll describe this in more detail on the next slide, but you sort your data in ascending order and you decide a stem, which is usually the last digit or the leftmost digit, uh, and a leaf, which is, or I said that the other way, or I said that wrong. There's a number of different ways you can do it. You decide on a stem which is everything to the left of the last digit, meaning the ones digit, and then a leaf, which is usually the ones digit, the digit furthest to the right. And then you write down all the different stems, and then for each stem you write the leaves in ascending order, and you include the stems even when there's no leaves. So an example of this for the chick weights data is the name of the weights. Previously we were only looking at the feeds, now we're looking at the weights. And the weights are a vector going from 108 to 423, I think that's in grams. So if I were going to create a stem and leaf plot for this data and I were going to do it by hand, I would first sort the data set of weights, 108, 124, 136, and so on. And in this case, R rounds to the nearest tens place when it creates the stem and leaf plot, so it rounds basically 110, 120, 140, 140, 140, several 140s, etc. And then it lets the first digit be the stem and the second digit be the leaf. So you see 108 gets converted to 110, so next to the 1 in the graph you see 1, 1. 124 gets converted to 120, so next to the 1 you see 1, 2, and then as I said there's a series of 4 that are rounded to 140, so you see 4 4s next to the 1, and so on. You repeat this for all of the different measures. And like I said before, I mean, there's not much reason to use stem and leaf plots at all nowadays, but you will almost certainly never want to use them. You will almost certainly never want to graph them by hand. If you want to create one in R, the command is called stem. If you say stem weight, it gives the stem and leaf plot for you automatically. The main advantage of stem and leaf plots, they're easy to create even if you don't have a computer. And in principle, they could be useful because they allow you to reproduce the data exactly if you don't round the way that we did on the previous slide. But the downside is for large data sets, you don't want to use them. It would fill up the entire page. And another downside is that histograms and box plots that I'll show you here in a minute are almost always more informative. And quick little side, when you create stem and leaf plots, sometimes you'll want to split the stem. R did this in the previous slide where next to this, where the digits 0 to 4 go to the right of one of the stems and the digits 5 to 9 go to the right of the next stem. Anyway. The next type of graph for quantitative data is called histograms. Again, hopefully you've seen this before and they're reasonably intuitive, but I'll explain this briefly in case you haven't. That the way you create a histogram is you divide the data into a series of intervals or bins. In this data set, it looks like they did 100 to 150, 150 to 200, 200 to 250, so on down the line. And then you basically do a bar plot the way we described earlier, giving the count of the number of observations in each bin. So here it looks like there's about 7 observations in the bin from 100 to 150, 10 observations in the bin from 150 to 200, probably about 16 from 200 to 250, etc. To create a histogram, typically R will do this for you, so you don't need to worry about it too much, but to give an accurate representation of the data, your bins need to be need to have equal width, and you want to choose an appropriate number of bins such that you want to choose enough bins such that you can see the shape of the data, but not so many bins that you just have 500 bars of height 1. So a usual rule of thumb is that you'll want 2 to the k greater than or equal to n, where n is the number of observations and k is the number of intervals. So here there's 71 observations, so we choose 7 bins because 2 to the 7 is the smallest power of 2 that's greater than 71. If in general you could just use the defaults in R and it'll work okay, and some bars may have a height of 0 if there's no data within a particular range. To create a histogram in R, the command that you use is called hist, and once again you can pass it the main parameter to create a header. The next type of graph is called a box plot, which could be a little harder to understand if you haven't seen this before, but basically when you plot a box plot, the line in the middle corresponds to the median. The top and the bottom of the box correspond to the first quartile and the third quartile, that is, the data points that are the observations such that 25% of the observations are less than the first quartile and 75% of the observations are lower than the third quartile. And then the little whiskers on the end go out to the most extreme observation that's within 1.5 times the IQR, or 1.5 times the interquartile range from the first or third quartile respectively. You don't see it on this particular box plot, but if there were observations outside that range, they would be plotted with dots. Recall the median is the middle observation of a data set. The half of the data is lower than the median and the other half is higher than the median. And similarly, 25% of the data is less than the first quartile, 75% of the data is less than the third quartile. And the interquartile range is the difference between the first and third quartiles. So as I said before, the line at the center represents the median of the data, and the top and the bottom of the box represent the first quartile and the third quartile, and the whiskers will extend the most extreme data point that's no more than 1.5 times the interquartile range from either the top of the box or the bottom of the box. And if there's observations outside that range, they're indicated with a single dot for each observation. So to create box plots in R, the command is called box plots. Here I'd say box plot weight, and once again I give the labels for the header and the y-axis as I've done earlier. And one really nice thing about box plots, if you want to compare a couple groups, is that you can plot several box plots side by side, which is useful if you want to compare the different types of chicken feed supplements. For example, with the chicken feed data here, I plot a separate box plot for each different type of feed. So you see, for example, the chickens that got casein had a median weight of a little under 340 with an interquartile range that goes from probably around 270 to 370, something like that. Meanwhile, the median for horse bean was around 150, the median for linseed was a little over 200, etc., etc. That's a good way if you have two groups, say cases and controls, you can just take a quick glance at your data and see if it looks like there's a difference between your cases and controls. And to do these side-by-side box plots in R, use the box plot command in R, and the syntax you go weight and then like a little twiddle feed. This is an expression or a formula object in R, where in general it means that you want to explain the variable on the left using the variable on the right. So here we're trying to explain weights based on feeds, so we plot a different box plot for each feed category. You'll see that notation again later in the course. And once again, you can give x-axis labels, y-axis labels, and headers if you so desire. So, as I said before, in R, when you say weight, and then a little tilde, and then feed, that's known as a formula. Usually means you're trying to predict or explain a variable based on other variables. The variables that we're trying to predict always goes to the left of the tilde. So in this case, you say predict weight based on feed, and we'll use this syntax again later in the course. So when should you use histograms and when should you use box plots? They're both useful. Histograms generally give you more information about the overall distribution of the data if you want to see if it's generally symmetric or badly skewed or how it works. That's harder to see on a box plot. Box plots allow you to immediately see the median and quartiles, which you may want to know, and they also do a better job of revealing like extreme values and outliers and things like that. And also if you want to compare two data sets side by side, that's easy to do with histograms. Doing it with box plots doing it with histograms is much harder. Well, the things to remember for today is that it's easier to see patterns in your data when you graph it, and you can graph categorical data using bar charts, pie charts, or dot charts. You can graph quantitative data using stem and leaf plots, histograms, or box plots, and different types of graph may reveal different information. It's a good idea to try a couple different types of graphs and see which is most informative. And that's a quick summary of the R commands for today that you can use to reference quickly if you forget which functions are used for which graphs. Another thing to keep in mind for R, all of these graphing functions take the parameters xlab, ylab, and main. If you want to label the x-axis, y-axis, or the header, which is something you should always do unless you're just creating a quick and dirty graph for personal use. You can also do formula objects in R using this little tilde. We'll discuss this in more detail later.